Hello, welcome back. Today we are going to learn how to factor quadratics. So far, we haven't learned any method of factoring that would apply to trinomial quadratics like this one. But if we could split up the quadratic into 4 terms, we could try to group it. However, to figure out how to do that effectively, we must first analyze the structure of quadratics. We know that they look like this in factored form, sometimes with a scalar on the side, so let's see which coefficients translate to which terms. Well, first we know that the coefficient of the x squared term must be d times f, or df, because they are the only combo that would result in x squared. Next we see that the constant term will be eg, for the same reason, but the x term won't be so easy. It will be the sum of ef times x and dg times x. This is because both combos would result in x to the first power. We don't have a clear b term, so to get one, we have to factor out the x from the middle two terms, like this. So we can see that the two numbers that we split our b term into, which are ef and dg, will add to the b term and multiply to defg, which has the same value as the a and c terms product, which is also defg. Armed with this knowledge, we can now attempt to reorganize this quadratic into a polynomial that we can group. I have left our work to the side if you need a refresher. So first we multiply a and c together, in this case 3 and 6, and we get 18. Next we list the factors of 18 to see which of them add or subtract to the b term, which is 11. First 1 and 18, which gives us 19 or 17, not 11, then 2 and 9, which do in fact get to 11 when added, so we split up 11x into 9x plus 2x. Now that we have a 4-term polynomial, we can follow our grouping procedure. There is no GCF that we can factor out, and the polynomial is in one variable, so we can just match up the adjacent terms and factor out their GCFs. Now that the binomials match, we can factor them out. And we are done. If that last bit was confusing, you should watch my previous video on grouping polynomials. Otherwise, let's do another example. At some schools, including my own, this method is taught using an x, so I will show its use alongside the main work. First, we multiply a and c to get 210. And for the x, we put it at the top, along with the value of b at the bottom. Next, we write down the factors of 210, which gives us a very extensive list, and we will see which of the factors will add or subtract to 29. Upon doing so, we will see that the pair we are looking for is 14 and 15 at the end of the list. So we split up the 29x into 14x plus 15x and write them on the sides of the x, right here and here. Then we factor out the GCFs from both the first two and last two terms to hopefully get matching binomials, which we did in fact get, so we factor them out and we are done. And just like every other way we have learned to factor, you can always redistribute the result to check your work. Now, let's discuss a shortcut that, while never necessary, saves so much time it might as well be. It only applies to quadratics of the form that's on the screen, the difference being that a equals 1, so we don't write it. But before we learn how to use it, let's derive it. Like last time, we first write the general factored form of quadratics, but this time, since a equals 1, both d and f must also be 1 to get just x squared, so we can remove that. And we will once again distribute it and factor out the x, so we get a simple a, b, and c term. This time, it should be a bit more clear how this is helpful, because we can see that the two numbers that make up the factored form multiply to the c term and add to the b term directly. So if we wanted to quickly reduce one of these quadratics, where a equals 1, we could simply list the factors of c and write the pair that also adds to b. Let's do an example to show you what I mean. We should immediately notice that a is 1, so we list the factors of c, which is 30. Now we go down the list, checking if any add to b, which is 17. Hopefully we rather quickly arrive at the conclusion that 2 and 15 is the pair that we were looking for. Knowing all that we do now, all we have to do is set up the binomials and put 2 and 15 there, like so. You probably understand what I mean about how time-saving this method is, as opposed to factoring the quadratic by grouping. The last thing I need to cover for this topic is very similar to something from the end of last topic, being the fact that you may once again need to factor out the GCF from the quadratic before you begin factoring it. This is particularly important here because sometimes a quadratic will initially have a non-1 a term, but it can be factored out to make the shortcut doable. The method we covered in this video is much more complex than usual, so here's a brief summary. First, factor out the GCF if possible. Next, you list the factors of C if A is 1, otherwise you list the factors of the product of A and C. Then you check which pairs of said factors add to B. After that, you put the factors into parentheses with X if you are doing the shortcut, otherwise split B up into factors of A and C. Finally, you factor the new polynomial by grouping, and remember that you can always check your work by redistributing. To finish this video off, let's do some comprehension questions so you don't forget. And here are the answers. Thanks for watching. I hope you enjoyed and learned something. Don't forget to leave a like and subscribe. See you next time.